Okay, so what we'll cover today is really going through the Ethernaut challenges, doing a walkthrough of those. And then we'll take a few security incidents that I would ask you to essentially investigate, and we can look at them essentially together. What I'm particularly interested in here is the 4 attack stages, like how did the attacker get funded? How did they prepare for the attack? How did they exploit? And then what sort of activity did they perform to launder the funds? And then we'll briefly talk about assignment 8 and 9. Could be that we end early today. Okay, Ethernaut challenge. The first one was fallback. Can that be read? Okay, well, sorry about that. Just open it up if you can't read it. So the goal of this particular challenge was to claim ownership of the contract and then reduce its balance to 0. So how invoke the contribute functions with less than 0.001 ETH. So your account has contributions, then send any value to the contract. The fallback function gets invoked either if you try to invoke a function that does not exist in the function hashes, or you just kind of do a transfer directly, and then you can do the withdraw. So here are the 2 functions that are kind of relevant. All right, next one is the fallout, where you need to claim ownership of the contract. Now the constructor has been deprecated the way this is getting invoked. So even if you do a fallout, I think you get a warning or a compile error. Now you have to use the constructor keyword. So this is less of a vulnerability with new contracts. Yeah. Call the fallout function. And you're done. Okay, next one. Coin flip. Marco Perea, you want to take this one? So the coin, so just to kind of go over this. So this is a coin flipping game where you need to build up your winning streak by guessing the outcome of the coin flip. To complete this level, you need to use your psychic ability to guess the correct outcome 10 times in a row. Block hash, block number -1, which is the previous block, right? So there's really 2 solutions. The one solution that Mark and Colin mentioned around you create a contract that essentially does the coin flip and only invokes this contract if it's winning, right? The other way you could probably do this as well is by submitting transactions at with a kind of high gas, so it gets included into the next block, and then you kind of have to off-chain do this logic, calculate it based on the previous block hash, and then basically at that point in time submit it to the mempool. I don't know whether anybody has done that solution, because that is a little finicky, right? Because now you're relying on the miner to pick up, and Gurley obviously the kind of the block time is pretty fast. So guaranteed is by having a contract that implements the same logic. What I would like you all to do is start investigating this particular. So we have 3 attacks. So this one is the DFX finance attack. Here is the attacker address. You don't, well, or you could also enter the DFX finance exploiter. And so what, and Duke, before you got here, basically what I'm interested in is getting information around how the attacker got funded. What did the attacker do at the preparation stage? So essentially all the activity between the funding and the exploit transaction. The exploit transaction itself, get a sense of what they stole and from whom. And then lastly, what action did they take for money laundering? And then, so kind of tools that you probably want to use is Etherscan. There's also the BlockSec Explorer, which makes it a little easier to track like transfer of digital assets across contracts. And then lastly, Forta. I would ask you to answer the question in terms of what did Forta identify on this particular attack? And so you go to app.forta.network, go to Forta Explorer, and then you can enter the address there. And then once we kind of have that all mapped out, then we can discuss whether monitoring would have given the protocol enough time to mitigate the attack, right? And then was the protocol in a position to mitigate? Meaning, did the protocol have a function that they could have invoked to essentially halt the protocol? And don't look at the analysis document yet. So basically, what attacker on the app starts advanced search. Essentially, you can search either by the address, or over here you can also search by the transaction hash. So let me just kind of paste the attacker address here so you see what that looks like. So basically, when you add the attacker address, you get all the alerts. Now there's going to be a lot of alerts here, and one way to kind of get a better view is start filtering alerts that are not that interesting. So omitted, address as native token, approval. So you can start essentially filtering, and then you get a better better sense. So we can also do large native out. And then one thing to keep in mind, the timeline is kind of reversed. So you really want to go to the end to really get a sense on what did the attacker do in the funding stage. More time, or you want to start kind of talking to it? All right, so funding. How did this attacker get funded? Where did the ether come from? So let's go to the last transaction on this particular. So there's the little ether that comes in, right? But let's look at the account that it came from, which is the 8D0347 address. There's only one transaction, right? And where did that come from, right? Internal transaction, Tornado Cash. So then let's look at Forta, this particular address. A lot of alerts. And you see a bunch of Tornado Cash alerts. Yeah. All right. So let's go back to our other account holder. So then what did they do in terms of preparation? Okay, let's look at that contract, right? So here we go to the contract. it is unverified, right? But now if we go to the opcodes, then we can start looking through the opcodes, and I'm just scrolling very quickly because basically what I'm looking for is addresses, right? And addresses look like this. This is the attacker address. This is not relevant, but here's an address. Could be, yep.
So that's pushing an approval. I mean, so I read that as, hey, I'm giving approval to the attacker address to operate on something with a thing that was off.
Could be. But here's an address. We don't know yet what it is. So there's a contract.
So it is in there.
That's right. So the attacker essentially did a mistake. Well, mistake. They don't care. Let me address what you said, Mark, because a very good point. So we have essentially, hey, there's Tornado Cash funding, and then a contract gets deployed on which some ML model triggered. And then within the contract, we have a set of addresses, right? You're right. At this point in time, we don't know whether this is actually going to be a contract that attacks the protocol. And I could probably create a contract, right? I could get funded by Tornado Cash. I could create a contract that looks like it's going to attack the protocol, right? I could probably create a contract that scores high on the ML model, and I could create a contract that contains the address of some protocol, right? And so to your point, that could be faked, and that could lead to a DDoS attack if there's automated incident response actions, right? Like if the protocol would have hooked up, hey, if I receive these alerts from Forta, I will pause my protocol. Essentially, nothing will happen anymore, right? And so you could certainly fake
That, like, until that gets resolved.
Yeah, that one, I'm not sure whether that's gonna work well because you have your contract already deployed on chain, visible to everybody. And so somebody else will swoop in and essentially execute the attack if you're getting blocklisted. Once kind of the ML model triggers, probably not enough evidence to pause the protocol. Because it could be a false positive, right? But what happened after this smart contract was deployed? So a large flash swap, reentrancy. Yeah, not a lot of information there. But I do recall that there were some. So, you know, the severity is set by the bot developer. So there's a wide range, but let's see here what we can see.
There was an anomalous transaction.
I'm just trying to filter the alerts here a little bit so we can go to the interesting stuff. Money laundering, Tornado Cash, blah, blah, blah. Okay. So here you have an asset drained. So an asset drained alert basically means contract has, 50,000 ETH, and the transaction results in all that ETH being transferred. So let's look at the transaction here. Oh, this is a block. Dang it. Asset, contract, transaction. So let's look at this particular transaction. Oh, so this is essentially happening when, so you have the exploit transaction here, right? And who's receiving the funds? The contract, right? Well, after the contract has the funds, the attacker wants to have the funds, right? And so there is a, so they transfer all the funds from the contract to the EOA, 2 million USDC right here. And that's when the asset drained alert triggers. But so, and a whole bunch of other stuff. Don't take the name from the code as the actual protocol. And the reason for that is a lot of protocols get forked. The code is not true. They get forked. So Curve is a protocol, and I may say, oh, I'm not going to start from scratch. I'm going to do something similar to what Curve is doing. I'm just going to fork that code and create my own protocol. And that's exactly what these guys did. They created the DFX protocol. But how that would have to get implemented, right? So positive reputation can only be assigned to a set of addresses, either EOAs and contracts that already exist, right? So it's not about new ones. So large lists, and basically now the protocol, when it gets called, will have to determine whether the message sender is in that list. How would you implement that? Okay. Yeah, ENS, that's interesting. I mean, whether some contract has an ENS address, so ENS is essentially the domain service on Ethereum. I think whether a contract has ENS could be a reputation signal. But think of like this contract here. There may be a function, let's say, deposit, right?
Well, like the allow list, it's just like.
Yeah, allow list.
So I mean, I think there's two answers. One, you could do an Oracle, maybe as a prototype to start with.
Yeah.
You probably want to get eventually to where it's just a hash, so that it's just like checking in your allow list, where you say,
Yeah.
hey, I want you to be, top 500 certified to work with my smart contract, or top 5,000, or top 10,000, and basically what the submitting contract should give you is enough that you can basically prove membership or not.
And then what's the data structure you use for that? Okay, perfect. Another use case for Merkle trees. Yay. Mark, system, could take whether a contract is verified as a signal to determine whether it's reputable. It doesn't necessarily have to be verified, right? You could have a contract that has been behaving well over years with thousands of transactions.
We've actually seen this play out in the news the past like 2 weeks. Is it more important to be verified or to have an actual reputation of, posts that are high value and are from the original person? One costs $8 per month. It allows you to be Elon Musk.
That's right. That's right. Okay, so we determined 3 contracts were attacked over a period of 2 hours. So now if you think about, and at this point in time now you basically have 3 key pieces of evidence, right? Already kind of suspicious funding, suspicious contract, contains the address, and now there is the first exploit transaction that actually drains assets. I mean, at that point in time, it wouldn't have prevented the entire attack, but it would have prevented the subsequent exploitations.
I'm curious how far apart the 3 exploits were. Because again, then you're getting to like pool distribution and how much gas you had in the transaction and like when like you're in a race at that point.
Yeah, it was an hour. And basically what the attacker did here is you see here they exploit, and then they actually start doing some swapping.
And then they exploit again.
Then they exploit again. And so this is
Chance.
so here 717, and then see it this one 727. So 10 minutes roughly.
You got it. Two. Maybe like
No, they usually send it to Tornado Cache.
But like before Tornado Cache?
Oh, before the Tornado Cache was around?
Yeah.
Yeah, they send it to centralized exchanges that had very poor know your customer processes, where right if you sign up on Coinbase today, they will ask, I don't know, copy of your password,
Yeah.
right? Back then you could just say, hey, I want a new account, username, password, done. Now you still have then kind of the problem, how do you get it from the exchange out to your bank account, right?
But then
That's right. And so here's the Tornado Cache transactions. That's right. So 21. So the other thing that could happen, again, they had USDC, they had ERC20 tokens, right? You could have potentially frozen at that layer as well. There's an interesting. That's right. And so let's assume it wouldn't be a ERC20 contract. It would have said curve. It is not curve because they would have said, no, it's not curve. So then the question is, that's right. And you have to go through the code. And sometimes developers, yep, it becomes an investigation just to identify the victim.
$2 multi-million-dollar.
That's right. I hope you all go off after this class and create these businesses.
Right here, ready to happen. Let's go.
I can introduce you to some VCs. So sometimes.
Small commission for the teacher.
Yeah, and I think every contract should have a section. Hey, if you find a vulnerability, email us at secure@blah blah blah. Right?